We are continuing to talk about comparing groups on a quantitative response, and we have started talking about inference. We began with the conditions that are necessary in order for us to make valid inferences, and all of these conditions can be summed up with the last bullet here. Residuals are said to be IID normal, that is, independently and identically normally distributed. So whenever you hear that there is a condition for valid inference in this situation, and that is that the residuals are IID normal, that actually encompasses everything we talked about. Independence, the fact they're identically normally distributed means that they have homogeneity of variance, and the fact that they're normally distributed means they're normally distributed. So all of the bullets that precede this last one are wrapped up in this final bullet. So assuming that we can make a valid inference, now what we should do is talk about what hypothesis we can be testing. The F ratio that we learned about can be used to test a null hypothesis of the equality of population means. Now, what about the model that we talked about? What about looking at multiple linear regression with a categorical explanatory variable and setting up dummy variables and getting coefficients and looking at the coefficient of determination? It's all the same. When we looked at that p statistic for the coefficient of determination, that's the same p statistic that we're going to look at when we look at the F ratio and test this hypothesis. In other words, stating that the model can indeed explain some of the variation in the response variable is the same as saying that the means are different than one another. They are not all the same. If the means are all the same, it means that the model is basically useless. The model will not help us understand anything about the response variable. So those are all equated. The alternative hypothesis, if we can reject that null hypothesis, the alternative is that there are some mean inequalities. Now, it doesn't tell us that they're all unequal from one another. If you have, say, 5 different groups, you could have the 5th group different from the other 4, and the other 4 be all the same, and that null hypothesis would be false, because the null hypothesis is that all the means are equal, and the alternative is there are just some inequalities. The F ratio will come from the F distribution with k-1 and n-k degrees of freedom when this null hypothesis is true. If the null hypothesis is true, we expect to get an F ratio from an F distribution with k-1. What does that mean? There are k groups, so k-1 would be the number of groups minus 1. In the example we've been looking at, where there are 3 groups, that would mean 2 degrees of freedom, and n-k degrees of freedom. What is that? That is the number of degrees of freedom that you'll see in the residual. So, in fact, because we're dealing with an F distribution in which the parameters are 2 different degrees of freedom, the first degree of freedom is associated with the mean square in the numerator of our F ratio. The second degree of freedom is associated with the degrees of freedom mean square for the mean square in the denominator of the F ratio. And so we often refer to this as the numerator and denominator degrees of freedom. The F ratio is going to be larger than we would expect when this hypothesis is false. So in a previous video series, I showed you some F distributions, but I thought it would be helpful to maybe do that again. So this is going to actually create several F distributions, starting with an F distribution in which we have a degree of freedom of 1 for our first degree of freedom and 10 for our second. So that's the way the F distribution looks. Remember that when you think of this F distribution as being a distribution of ratios of mean squares. Now, we only in one study have one ratio of mean squares, so how do we end up with a bunch of them to create this distribution? The sampling distribution method. We sample, we calculate the mean square for the numerator and the denominator, we calculate the F ratio, and that's one F ratio. Then we sample again and again and again and again. And all of those F statistics, all of those F ratios will be in a distribution that looks like this if the model is useless, if the model has no effect. And we just learned that that's the same as saying all the means for our conditions are the same. So when those mean squares for the numerator and denominator are estimating the same thing, meaning that there is no treatment effect, we expect to see a ratio near 1. It kind of depends upon the degrees of freedom, how close to 1. You notice here that the most commonly occurring value is more like about 1/2 here, but 1 is still very popular. What happens if you get an F way out in the tail? Well, it could be that you got an F out in the tail, even though this is the right picture, but the other possibility is it's the wrong picture. So whenever we're calculating our p-statistic, we're looking at a p-statistic based upon this distribution that is drawn under the null hypothesis. So we're looking at the possibility of getting the data if the null is true. And when that possibility of getting the data when the null is true, and we actually do get that data, the null could be true, but what we decide to do, our decision is to reject the null hypothesis and conclude that there is a difference in the means. Let me do a couple more F distributions. Here's one with 3 and 200 degrees of freedom. And so it would look like that. And notice that the peak is at a little bit different place. And let me go ahead and just run the rest of these. So if I will create all these distributions, you see that they're all a little bit different, but they have a very similar form. And that one in green there is associated with 6 and 200 degrees of freedom. And in that case, the F ratio that occurs most frequently is very close to 1. So what did we have in our study? Well, let's take a look. Let's go back to the that particular notebook. And here it is. Let's go back to the ANOVA table. There's our ANOVA table. And so we are looking at 2 and 222 degrees of freedom, and we got an F value of 6.2. 2 and 222 degrees of freedom. Let's go back and look at that. 2 and 222. So I'm going to go ahead and change this first one to 2 and 222 degrees of freedom. So let's go ahead and construct an F distribution with 2 and 222 degrees of freedom. Looks a little bit different than what we've been looking at. This is what it looks like. And so that part that we've been seeing come down near 0, it actually comes straight up here. If I don't have this program to draw a line here, but there would be a line drawing straight up here and then coming down from that point down and trailing off. Now, our F statistic that we actually observed, let's see, what was it again? It was 6.22. So on this picture, that 6.22 is way off on the right side, way off the end of this picture. The area beyond that 6.22 is right here in our P statistic. It's 0.002. As a consequence, we would reject the null hypothesis and conclude that there are differences in the means in the population. We knew there were differences in the sample. We knew that right near the beginning when we calculated these means, and we got 25 and 37 and 39. Now we conclude there are differences in the population. Of course, your question's going to probably be, all right, which ones are different from which? And stay tuned. We're going to look at that in a later video. But right now, all we're saying is we know there are differences. We don't know where they are. We don't know which groups are different from which other groups, but we know that there are differences. And remember what this means. It means, in terms of our research question, that the worldview does seem to have an influence. We can't say it's causal. This is not an experiment, but it does seem to be associated with the risk perception for being in an airplane. Remember that we have k minus 1, n minus k degrees of freedom. I should have shown you that back here. Where is that? No, there's that ANOVA table. So 2 degrees of freedom, that is k minus 1, number of groups 3, minus 1 is 2, and n minus k, 225 observations minus 3 groups, that's the residual. So 2 and 222 are the degrees of freedom associated with the numerator mean square and the denominator. So the F statistic under the null hypothesis, when the null is true, is distributed like an F distribution with 2 and 222 degrees of freedom. Our F ratio is substantially larger than that, and so we suspect that the null hypothesis might be false. We don't know that for sure. That's not what we're actually assessing here in our probability statements, but what we are saying is we've decided to make a decision that when we got real unusual data, if the null hypothesis is true, that we'll reject the null hypothesis, and that's what we did. Okay, in my next video, I'm going to take on a challenge and construct a report.